all I did was I created an x and a y axis. Okay? And then I put the compass thing here, right? Here, so that I could make this arc from here to here.
So the units don't matter?
Not really, because ultimately we're talking about unit circles. In this particular case, I then counted the box and found, oh good, this is 24, and this is 24, so it worked out pretty well. Okay? And then I wanted to start putting in some angles. And the first one I did was 45 degrees. But I didn't use the protractor. How did I do it? Yep.
Straight down the middle.
What does straight down the middle mean? Down the middle of what?
Down the middle, like it's like between both sides, right? Because it's like 45, half of 90.
Right, but how did I find half of this? It's not like I could have, I guess I could have folded it in half and done it, but that's not what I did. Yeah.
So this is graph paper. You could just go corner to corner of the box that's in the origin.
Yeah.
Right. Do you understand what he said? Go ahead.
Like you can use slope.
You can use slope, and we're talking about a slope of,
Of a line.
right, and the slope of this line would be 1. And if you learned trigonometry here, the way we taught trigonometry here was we first linked tangent and slope and said they were the same thing. Does that sound familiar? Slope is rise over run. This is right, some number of units out, some number of units up. Right? The slope right here is 1 from, as you said, from corner to corner to corner. Right? Everybody okay with that? We call this rise. We call this run. And that works really fine until the angle looks like this. And then which one's the rise and which one's the run? Is it this one? Is it this one? Is it this one? I don't know. So the way we teach trigonometry here is to start out with the idea of slope, rise over run, and then to give you new names for stuff so that you can refer to the sides of the triangles with names that don't depend on their orientation. In other words, rise and run depend on gravity. In order for rise and run to count, you got to know which way is down. Right? If I said to you, okay, this is the triangle right here, and this way is down, you could do rise and run. But if I said to you, okay, look, here's the angle right here. We're going to describe this as, this is the hypotenuse. This is the opposite side. This is the adjacent side, right? Because this is adjacent to the angle we're talking about. This is opposite to the angle we're talking about. So instead of calling this rise over run, we're going to call this opposite over adjacent, and that will be tangent, and the tangent of 45 degrees is equal to 1, and because I know that the tangent of 45 degrees is equal to 1, I know that this has to be 45 degrees. Okay, right here.
I just need a refresher. Can you explain the difference between tan, cosine, and sine?
Well, let's just start with tangent. And what I said is that the tangent of any angle is equal to the side opposite the angle divided by the length of the side adjacent to the angle. Okay? That's right this second, that's all you need to know, because that's what we're talking about. Okay? So I have redefined this. Instead of rise over run, this is now opposite, this is now adjacent. This was the angle that we were using as a reference point. Okay? And because every right triangle that I make, whether if I make a right triangle here, or I make a right triangle here, or I make a right triangle here, right? All those right triangles are going to be similar triangles, right? You remember similar, right? Similar means that they have the same size, the same shape, but not necessarily the same size, okay? Sort of informally, that's the definition.
Are they proportional at the sides?
Well, they would have to be, wouldn't they? Because, and then we said why. Remember, one of the things you could do to tell that two triangles were similar was angle, angle, right? So if I keep this angle constant, and this is always a right angle, then this, and this, and this, they all have to have proportional sides, which means the ratio is always going to be the same, which means the tangent, because all we're talking about in terms of tangent, the way I just defined it, is the ratio of sides, right? So if the ratio of sides is always going to be the same, then for any given angle, making a right triangle out of it, the tangent will always be the same. Thinking about this in terms of slope, right? You always learned that it didn't matter which 2 points on the line you picked. You could have picked this one and this one, right? Or you could pick this one, and the slope would be the same on the line. You remember that from Algebra 1? Right? The idea is if the slope changes, it's not really a line. Right? If the slope changes, it means it went up this way and then went off that way. Again, does this make sense? Yeah.
You got 1 for 45 degrees because the slope is 1/1.
Right.
What if it's something else?
Well, if it's something else, then it'll be a different angle measurement, and we'll get to that in a minute. Okay? Here's your arc. We said the other day when we were talking about the unit circle, this is pi over 2. So this has to be pi over 4. I wanted to do a 30-degree angle, and I know that if I'm doing a right triangle that has a 30-degree angle in it, it's a 30, 60, 90. And that means that the side opposite the 30-degree angle has to be half of the hypotenuse. Does that sound familiar? Okay. Because of the ratios that come with special right triangles. I counted and I knew that this was 24 and this was 24. So I knew that all of these had to be 24 because that's the definition of a circle. It's all the points that are the same distance from the radius. So all I had to do was figure out where is it that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Where is it that this side over here would be half of this distance over here? Right, but on this particular thing, right, since I know this is 24, I know that this height has to be 12, right? And here it is. This is 12 from here to here. What's that?
It's 21.
No, it's from here to here is 24.
Like the line going up.
This line going up here?
Is that the x value between 1?
Oh, but that doesn't matter. I'm talking about the height of it. The length of this line is 12, right? And the length of this line is 24, right? So basically what I have is a right triangle here with a 30-degree angle, and I know it's a 30-degree angle because this is 12 and this is 24.
How do we know that one's 24?
Because it's a circle, and here it's 24, and here it's 24, so everywhere all around here it's got to be 24. Okay. Jennifer, you asked me about the other ratios, right? Okay. So remember, if all the sides have the same ratio, right? This ratio to this is going to be the same no matter what the size of the triangle is. I'm talking now not about the ratio of the far side to the adjacent side. It's not opposite over adjacent. This time it's opposite over hypotenuse. What do we call that? Well, that was the way we defined the sine, right? The sine was equal to the opposite over the hypotenuse. And because of what we know about these triangles, if I have a special right triangle, the sine of 30 degrees, whoops, that's silly. That's what I meant. The sine of 30 degrees has to be 1/2. Everybody okay with that? It's got to be, because that's the ratio of the sides of a special right triangle. So I know that this is 30 degrees basically because the sine here is 1/2. Questions? Yes?
How do you know like which angle to start with? Like,
Well, I'm using this angle right here. Is that what you mean?
yeah.
How did I know what angle to start with? Because I didn't actually start with an angle. I was looking for a 30-degree angle. And what I started with was, I know the sine has to be 1/2 because of the special right triangles. I know that this is 24. So if I can find the place where the radius intersects the circle at a height of 12, I got myself a 30-degree angle. You okay with that? Okay. Stay with me, because this is the unit circle. Okay? Notice that when I talk about this, I'm no longer talking about 12 and 24. I could have been talking about 15 and 30. I could have been talking about any two numbers whose ratio is 1/2. Okay? So in other words, if this is 1, this is 1/2 unit circle. Okay, so now let's turn this around for a second. What if I wanted 60 degrees? Right, there's 60 degrees. Right? There's a right triangle. This is still 24. What do I know? What side do I know? Yeah. That what's going to be 12? Right, that this right here has to be 12, right? That means that if I count over here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then I walk all the way up here to where it intersects the circle, and I connect these two dots right here, this angle right here has to be 60 degrees. Yes. Okay? It's got to be 60 degrees. Why? Okay, because, and Jennifer, this is the other one, the cosine of an angle, right, is equal to the adjacent over the hypotenuse, which is what I've got right here, adjacent, hypotenuse. So the cosine of 60 degrees has to be equal to 1/2. Now comes the really weird and interesting part of this. Okay? What I just described about this circle is true, right? That no matter what angle I pick, let's say, just for fun, this point right here. Okay? All right? And now let's say that I'm looking at this right here. Okay? You with me? And I want to know, what degree measure is this? Well, I should be able to figure it out. I picked this particular point because it looked to me like it was going through this the crosshairs here. This is where it's 23, right? And this is where it's what? 1, 2, 3, 4, 5, 6, 7. Okay? Yes? Okay. So the distance from here to here is 7. The distance from here to here is 23. And if I wanted to find the sine of this angle, wouldn't it be sine of theta? Wouldn't that be 7 over 24? All right. No, it would be 23 over 24. There we go. 23 over 24. There we go. Sorry. Right? And the cosine of this angle would be 7 over 24. We okay with that? Does that all make sense? Okay. Who has a calculator that does trig functions? Pull it out. You're going to help us out here. Right? I mean, this is, what is this? This is the y-coordinate divided by the hypotenuse, or the radius, and this is the x-coordinate divided by the radius, right? Okay, so 23 over 24 is 0.96, okay? And if you did the inverse sine of 0.96, what do you get? The inverse sine of 0.96 is equal to what angle? You got, what'd you get? 73.7. Okay, so in theory then, this should be 73.7 degrees. Okay. Now, let me ask you to do this. Take 7 and divide that by 24 and do the inverse cosine and tell me what you get.
You divide 7 and 24 first.
Yeah, because I want to know what this is as a decimal.
73.
73 even?
0.04.
73.04. So in other words, based on my drawing here, I know the measure of this angle within, I don't know, what, 0.66? It's somewhere in there. It's somewhere around 73 or 74. Yeah, you had a question?
Yeah, I figured it out.
Okay. So I now know this degree measure right here because I know the coordinates here. Well, and yeah, let's do this. Do you know how to change your computer, your calculator to radians?
Yeah.
What would 73 degrees be in radians?
See, that's what I was like doing.
It was
and then-
1.2.
How much?
I think it's like
1.27.
Yeah.
Okay, so that would make this 1.27 radians. Right? From here to here. Does that make any sense? I mean, here we got a fraction, and here we have a fraction, a fraction, a fraction, and here we have something greater than 1. How is that possible?
Because that's what pi over 3 is.
Right, pi over 3 is pretty close to 1,
Yeah, that's what I'm saying.
right?
And then it's a little above.
Right. Pi over 2 would be pretty close to 1.6-ish. So somewhere between there is 1.27. So actually that does make sense, doesn't it? Now here's the final, the coup de grace here, the exciting moment of everything. Let's assume for a minute that I was talking about a unit circle and that the distance from here to here whatever this is right here, this distance is 1. Okay? It's a unit circle. Whatever this distance is right here, this is y, right? But it is also the length of the opposite side. Right? And this right here is x, but it's also the length of the adjacent side. So far, so good?
Yes.
Well, guess what? That means that the coordinates of this, which normally we would have said were x, y, okay? Here we go. This has to be x, which is the same as x over 1, which is the same as adjacent over hypotenuse, which is actually the same as the cosine of theta, which would be this angle right here. Right? And y, right, this distance right here, the same as the opposite side, is equal to the same as y over 1, which means it's the same as the opposite side over the hypotenuse, which means this has to be the sine of theta degrees. Everybody with me on this? Yes.
Is it both the same angle for theta?
Yeah, it's this angle right here. Whatever this angle is that's created by this segment creating this triangle, right? Yes?
What's the not the variable, but what's theta again? Like, what does the actual symbol look like?
It's this. It's the circle with the line through it. Okay? Yeah.
So once we find that angle, we can do that.
Yeah. Okay? We can do whatever we want. The interesting thing here is that once you're dealing with a unit circle, this is cosine, this is sine. And over here, right, what did we have to do to get cosine and sine? We had to divide it by 24. In other words, we had to make the ratio of a unit circle. Right? This was 24, so we had to divide these by 24. All right? Now, do you remember the other day we were looking at the idea of a wheel, right? We had a wheel, radius was 7, down here 6 was where the water level was, and we were watching a point move counterclockwise, and we were asking for the height from the water of the point as it went around the circle. Well, what did we just say? We just said that, right? This distance right here is going to be related to the sine of this angle right here. And when I say related to, I mean, well, we're going to have to take this distance right here, figure it out, and then add this distance over here in order to get the height from the water. Yes? But whatever it is that is the sine of this angle, as it changes, so will our answer. And we said that just from our own reasoning, we could tell that the graph we were going to be dealing with would look like this. Right? This then turns out to be the graph of what happens. Well, wait a minute. We've only defined, unfortunately, we've only defined the sine from here to here. Right? What's the sine of 0 degrees? Yeah, right? Sine of 0 degrees is 0. Okay. What's the sine of 90 degrees? What's that?
Oh, I probably have it on there as well.
Yeah? What's it say? Ratio's 1?
Yeah, it is one.
Sine is y and 1.
Okay. So then that means if I were dealing with a unit circle, right, this up here, the best it could be would be 1, right? And the lowest it could go would be 0, right? So,
We go to -1, right?
well, not really, because we haven't defined sine.
But like on the ground.
Aha! Exactly. And this is why we need to redefine sine so that we can figure out what's the sine of this angle. What's the sine of this angle? What's the sine of this angle? And you just pointed out that in order for this to really work, we're going to want this measurement here to be a negative number, aren't we? So that we could subtract it from 7 instead of adding it to 7, so that we can get the height of the circle, the height of the point on the circle, right? Same here. We want this right here to have the same sign as this one over here, right? Because they're going to be the same height. So if we're defining it that way, we're going to want this height and this height, since they are the same, to represent the same sign here and here, so that when it gets past 1, in other words, let's say we started here and we went around to here, right? This is where here is, this is where here is. So it went all the way to the top, that was our maximum, and then it turned around and started coming back down again. Okay. Well, if you remember, we decided that this right here was the reference angle for this angle, right? That if we use the sine of this reference angle to define the sine of this angle, we got ourselves a system that works. Everything becomes, it all fits together nicely. All we have to do is call it. We have to define it. So we're going to actually change the definition of sine and cosine so that we are able to find the sine and cosine of this point as it goes around the circle and then suddenly finds itself down here below the x-axis in the first quadrant, finds itself over here in the fourth quadrant, finds itself in the third quadrant, right? That's what we're going to do. This is directly out of the book. It's on page 74. Okay? This is on page 74. And what this is a redefinition of sine, cosine, and tangent, and an extension to the other 3 ratios, which is the reciprocal of sine, cosine, and tangent. There are 6 possible ratios. Now we're going to deal with all of them. With a right triangle, we define them all as hypotenuse and opposite, adjacent and opposite, all that stuff. Over here, what's going to happen instead is we're going to deal with the vertical coordinate divided by the radius, or the vertical coordinate divided by the horizontal coordinate, etc., etc. That's our new definition of sine, cosine, and tangent, as well as cotangent, secant, and cosecant. And the idea here is that if you do it this way, what you're getting are the sines, cosines, tangent, cotangent, secant, and cosecant of the reference angles.